Good evening, everybody. My name is Blake Blaze. I'll kind of be the MC for tonight. Tonight we are covering our third installment of data literacy in the wild, and this time we are taking a look at climate change. This is probably, it's tough to make a subjective claim like this, but probably the most important of the topics we've covered so far. Our first one was on sports. Our second was on public health. Would definitely encourage you to check the recordings of those out on our website, but really excited to take you through a couple of data sets tonight that are looking at climate change and really presenting ways that students can work with this data that is increasingly something that young people think about and care about. So I'm joined tonight by Dr. Aaron Reedy, the co-founder of Data Classroom. He's a former high school science teacher, spent 7 years in the Chicago Public Schools, then went on to get his PhD in evolutionary biology at UVA, and along the way, built Data Classroom. I've been lucky to work with him for the past 3 years in kind of a jack of all trades role, for which time I was a cyber intelligence officer in the United States Navy. We worked with a lot of data in that capacity. And before that, I was a high school math teacher, and really it's been a natural fit to work with Data Classroom. And I've loved every second of it.
Boys and girls? Yeah. I got a thank you for Thomas. So,
quick schedule of events. We're going to talk about climate change data and some of the important pedagogical aspects of working with climate change data. And through a data set that looks at cherry blossom blooms in Japan going back centuries, into the 9th century. Some very cool data there. Then we'll look at a MyNASA data set that we made in collaboration with MyNASA Data that's measuring surface anomaly temperatures. And then, time allowing, we'll take a look at a digital data nugget. We've been lucky to work with data nuggets over the past couple of years, which some of you might be familiar with. We've got a cool data set that's got a pretty clear picture about what the impacts are of increasing temperature on the phenology of plants. Here are the 3 data sets we're going to be working with. So we totally encourage you all to make a Data Classroom account if you haven't already, and that way you can work with the data sets as we work through them ourselves. I've got these links here as a reminder to myself to drop them in the chat. All right, so a quick discussion about some of the pedagogical aspects of teaching data science. The Virginia Department of Education has put together a really good set of standards for teaching data science, and the different strands they've outlined across these different principles are using context to help students appreciate the importance of what they're working with, and that's what we're all about at Data Classroom. That's why we're using these real-world examples we've distilled down into language and activities that we think are appropriate for classroom settings. It's obviously important for students to learn data literacy and be able to identify bias in data sets. We talk about that in all of the lessons in our resource library, where we give a little bit of background information about where the data came from, and then also how the data were collected. And being able to identify and appreciate how the data were collected is really important for how we impute the importance of the data we're looking at. Next piece, this is where I think Data Classroom really shines, is focusing on communication skills. It's important for students to be able to receive data and be data literate, but we really want them to be able to communicate the results of their own data sets or data that's out in the world around them. And with Data Classroom, we make it easier to use visuals to help communicate and tell a story around data. And then modeling and computing are pretty straightforward. We'll cover some aspects of that tonight, using graphing as a gateway to statistics and being able to actually work through the data sets to see what they mean. So we're going to try and cover 3 data sets here tonight. That is not the entirety of our data sets on climate change. We'd encourage you all to check out our resource library, where we have several other data sets related, whether you have students or whether you're personally interested in climate change. I should say I'll send this slide out to everybody later on, so don't worry if I'm moving too fast for now.
Yeah. But just reset it.
Hey.
If you don't know what it is, it doesn't matter. That you might as well just reset it.
Blake, do you want to go ahead and see if you can mute mics?
You know how to reset it?
I'll go ahead and mute.
Yep. And if you make me a co-host too, then I'll have some of those controls. But okay, well, thanks for the introduction and setting the stage. We're going to dive into a couple of data sets here, and the first one that we're going to go through is a data set that I think is just really cool that it exists. It's this early spring in Kyoto data in Kyoto, and this data set has been collected over a very long period of time. I believe it's going back to the year 812. And in Japan, they've been fastidiously recording the date of the first full blossom day of these cherry trees in Kyoto. And that full flowering date is defined when 70% of the cherry blossoms are open. We can ask some questions about climate change, particularly does it look like climate change is having an effect on data first flowering over this time period? And we can do that mathematically with a technique called regression, which many of you are probably familiar with. And we can visualize that through a line of best fit. So with that, I'm gonna jump over and open the data set. So bear with me 1 second, and I'm going to, Blake, it looks like you did make me the host. Thank you. And I'm going to pop up my screen so you all can see I'm in the data classroom resource library. From any screen within the app, if you're logged in, this browse tab up here on the purple bar where you see I just clicked and got the drop down menu. And I went to resource library to look at the data sets in the resource library. Each of these tiles represents a different data set within the library. We've got them tagged with those orange and beige tags, so you can see what the topics are. You can also see the grade levels in the purple tag. And up here in the text search in the upper right, I'm gonna put in early spring, and I started typing it and quickly narrowed the field down to this early spring in Kyoto, cherry tree blossom dates and historical data. And I'm just gonna click on the open data set. If you click on the open lesson plan, it will take you to a web page, which is like the lesson plan preview. But I wanna open up the data set within the Data Classroom web application so we can explore this data and look at it more in depth. For those of you who are new to Data Classroom, when we say data set, we are talking about the table view, which you are looking at now, and you can scroll through the data. We are also talking about the graph view and the assignment view or the attachment view. And I'm gonna pop open the assignment in another window over here. So I'll have two tabs open. One of them will have the assignment open, and it is loading right now. This is the student-facing assignment, and all of the data sets in our resource library that are ready to teach or digital data nuggets will follow this format where there's some background information and there's some information about the data set, and there are the variables are defined. And this is the kind of metadata that students will need to have at their fingertips to be able to make sense of the data. And then there's also the graph tab. So I'm going to pop over to the graph tab right here. And this is the heart of the Data Classroom tool. This is where we visualize things. I'm gonna start out by plotting full flowering date here. And so I plot that, and you can see each observation is a different data point on this dot plot. And remember that each observation represents a different year. So these are years going back to the year 812. And so you can see all of the data points. We could first do things like add descriptive statistics to this. And I'm going over here to the control panel at the right, and I'm adding descriptive statistics. And so we can see a mean and standard deviation there. If I want to view what that mean is, I'm going to check this little box that says values at the right. We can see that the mean date of first flowering is 104.6. And again, these flowering dates of the year, January 1st is day number 1, January 2nd is day number 2, and so on in chronological order. So a higher number means flowering later in the year, a lower number means flowering earlier in the year. We could also really quickly, look at these as a histogram. So, this and this are two different ways to look at the same set of numbers. And we can see, where the mean is just under day 105. So what did I say? Day 104.6. And you can see that it's more or less normally distributed around that mean when we're looking at the sample. It may be slightly skewed to the left, and I could turn up the resolution in number of bins to see if that reveals anything different. So I made those bins into units of 4 days, and we can see that I don't know. I actually don't detect much of a serious skew here. If I overlay the normal distribution on top of it, you can see how it more or less is normally distributed for that time period. I'm going to go back to the dot plot version of this, and I'm going to add another variable. I'm going to add this variable of year. And so we can see the data points across the sample here. We've got this nice sample of historical data, going back more than 1,000 years into history. And a question you might ask yourself is, how is the date of full flowering changed over time? And so we might want to do something like, add a regression line to that, and we could look at, the overall trend in that time period. And my first impression when I look at that is that's fairly flat. And we can look at some of the parameters of that. Like we can look at the slope of the line, which is, a very, very small negative number. So it's a relatively small slope, and the R squared value is 0.002, indicating that less than 1% of the variation in flowering date is explained by year. And so all of this is looking like evidence that this full flowering date hasn't really changed much over time. I'll point out, another way you could look at these data, you could do, instead of a regression line, you could connect the dots with lines, and I might even choose to hide the dots because there's such a density of data. I might even go into the appearance menu, and I could try to turn down the width of that connecting line to see if that can give it, any more clarity, but it doesn't really. We can see that, there's a lot of variation. You can maybe start to see some sort of trends within the data periods when it's trending down or trending up, but for the most part, I don't think that really dramatically changes the way that I'm looking at the data. So I'm gonna actually go back to the regression line for a second and look at the data this way. Now, with these data, one thing that we might do to try to get a little bit more clarity on trends and ask our question of, does it look like climate change is having an effect on flowering date over this time? I might add this categorical variable of time period. And so I'm going to click show to that, and I'm going to add this as a third variable. And if you look at the control panel at the right, you can see what's currently being displayed in red. So I got year on X, flowering date on Y. I'm going to put time period on Z and break this out into two segments, in pre-industrial time period and post-industrial time period, which I believe is everything from 1850 onward. And when we look at the data this way, it's a bit interesting looking, and it looks like, as we look at the blue, that it does look like it's trending downward over that time. And if I go ahead and I want to do a separate line of best fit for each group, like I add this group by Z, when I check this box, we get a green line for the pre-industrial period, and we get a blue line for the post-industrial period. And now, mathematically, what we can do is we can compare slopes here, but just visually, we can also compare slopes. And this is, one of the things that I think is really cool about exploring data with digital tools is you can really quickly do things to, subset it or visually subset it. we could also exclude this and essentially make two separate graphs. So if I come up to time period and I click this values box, we could have the option to exclude the pre-industrialization data completely by checking that exclude box that I'm doing there. And now when we go back and look at the graph and we look at just the post-industrialization data, we get our graph scaled to a different range on Y, but even scaled more appropriately to get to the relevant range, we see this kind of, downward slope. And it's not a particularly tight fit to the line. The R squared is 0.285, but still that, this change in time explains roughly 28.5% of the variation in full flowering data. That's pretty significant. It's almost a third, approaching a third of the variation looks like it's explained by this change over time. This becomes fairly strong evidence for climate change. And Veronica, thanks for your question there. Can you do this for the pre also? Absolutely. So I'll go ahead in there and I'll exclude post and I'll leave pre-industrialization time period in there. And when I do that, you see perhaps a slight upward trend, but the R squared value is still relatively low, much lower than it is for the post-industrialization data. With that R squared of 0.016, looks like less than 2% of the variation is explained by change over time. So this I think this data set is a good example of one, the power of a long-term data set, but two, how exploring that data graphically can actually reveal some truths that are maybe even more sophisticated than a student might have mathematical ability to pull out through modeling alone. But looking at it graphically, I think this is something that students across a pretty broad age range can see and see how they could use evidence in the data to support a conclusion. Blake, did you have anything you wanted to add, or are there any audience questions?
No other audience questions for now, but one thing that I like in having worked with some high school students on this particular data set in the past is that they'll ask the question of why 1850, and this is a good exercise because you can make these visual changes that are so striking, but then you need to justify that. Like this is what like real discovery requires. You need to think a little bit more than just like giving exactly what the data show you. You need to appreciate the context, right? Like we know that 1850 is the right time to demarcate that because all of a sudden humanity went from producing almost no greenhouse gases to like 10 times that number. So that's like how getting students to justify that decision is the higher order data thinking we want them to do, instead of like, okay, I made a graph and then letting that be the end of their analysis.
Yeah, absolutely. And it's I think it's also great too, because it can tie into, this isn't just a science data set. This can be a historical data set that you're discussing in a history class as well. It's something that can connect, and I think it's also something that even when sort of faced with this without giving them the context of, they might, even if you change the name of those variables, just to like before 1850, after 1850, and didn't give away that the fact that it was around the time of the Industrial Revolution, I bet in a room full of high schoolers, you would pretty quickly get, a few of them to suggest that, and have them kind of come to that conclusion on their own. So, all right. Well, with that, should I move on to the next data set, or is there anything we want to dig into in this one a little bit further?
Yeah, I'll put that to the chat. Are there any questions about data classroom functionality or about this data set? I'll give you 2 minutes to be brave and either unmute yourself or put something in the chat.
Sure. Okay, and I will, I'm going to stop my share for a second.
Can you, as the teacher, change the label of the pre-industrial and the post-industrial? Like I haven't worked with your data set, so I don't know this. Can you change that name?
You can, yeah, you can. I can show you how to do that. let me just share my screen again really quickly. Yep. So you can, and I guess one sort of just technical thing, any changes you make to a data set, you can save as a property of that particular data set. So for example, if I click this save a copy, this blue button over here on the upper right, and I'm going to just add a simplistic title, for my class. So I'm now taking this, and I'm anything I save to this, I can push this out to my class and have them work with this data set. But if I went into this time period, and I'm just going to go up to this little values box by this variable of time period, and I could change these labels. I could just make them simple. I can just call this green and blue for now, if we don't want to reveal anything. And then on the legend, I've got just green and blue there, and we could have the students do the brainstorming and do the thinking to get there. And again, once I save this, now this file that's my copy is mine. And if I want to share this with my students, I can do this from here, this little hamburger menu on the left. I could pull this out, and I can go to the sharing, which is about halfway down the slide out. And I can make a link to this. So now I've got this shareable link to this data set, and I could give that to my students. And if they'll log into Data Classroom, they can go with that link, they can go directly to this data set, and they can start working on, that copy that you shared with them, rather than the generic copy that they could find in the resource library. Yeah, good, excellent question. Thank you.
I just wanted to point out too, Christine, thank you for the question, that you can personalize basically every aspect of this data set to make it meet the needs of your students or your class. So in the assignment tab, you can modify that to add or remove questions if you don't like the activity that we recommended. Just might. Yeah,
this is an embedded Google Doc, and with this edit pencil, you can create your own copy that lives on the Data Classroom Google Drive, but you can change anything you want about it. So you can even start, in that same way, you can basically create stuff from scratch. You can add additional attachments to it, slideshows, and then of course, like Blake said, you can change this document any way that you want. Well, cool. Okay, I'm gonna stop my share while I get us back to the slideshow, just so I don't make everyone dizzy as I'm whipping through slides here. So with that, I will share this again. So sorry, 1 second. Okay, so this is the data set we went through early spring in Kyoto. You know where to find that now. So next data set that we're going to go through, this one is called Feeling the Heat. And this one is one that we made in collaboration with the folks at MyNASA Data. MyNASA Data has a wealth of data sets publicly available that NASA has been keeping for quite some time and is always adding to. Sometimes it can be a challenge to find what's interesting or make it accessible to your students. That's what we set out to do with them when making this Feeling the Heat data set and activity that goes with it. With Feeling the Heat, this is another case where we're going to use an additional categorical variable to add context, very similarly to what we did before with that early spring in Kyoto. And we're also going to talk about some changes that we've made to the graph that are already saved in this version, and talk about how the art of graphing can help communicate a story. So that when I say the art of graphing, talking about things like point sizes and colors and ways to subdivide your data, things beyond just like the basic rules for the components of a graph. So just to give you a little bit of context, this is historical data that NASA has stitched together from a variety of sources. the more modern part of this data set has been collected via satellite. And this is data stretching from January 1880 to March 2021. And it's a subset that we created of a much larger data set. And we focused just on 3 locations at each of 3 different latitudes. They have data on MyNASA data for literally like every spot on Earth. And we just picked some subsets that illustrate the trends you'll see in the larger data set. But part of the reason we did that is to make it more accessible to students. It's not always friendly to work with a data set that has 600,000 rows and 85 variables in it. So we cut this down to make it a bit more manageable. It's still, a substantial number of data points you'll see just from these 9 locations, or sorry, 9 locations, 3 locations at 3 different latitudes. And so you'll get a taste of, how big this would be if it was literally, a representative sample from everywhere on Earth. It would be quite a bit larger. So with that, I am going to just flip over to Data Classroom again. And sorry, I swear this is not my first.
Aaron, if you click the link, it should just take you to it from the.
Cool. Hold on. Just from there, we'll just jump straight in. There we go. So that is loading here. So this is the feeling the heat data set. So if you search this by the text search in the upper right in the resource library, you can come here. I think Blake put the link in the chat as well for your convenience. So this is the feeling the heat data set. If we go, and I'm just going to pop over to the graph view. And we're just going to kind of work through the analysis that's done in this data set. I guess the first thing I want to do, just to give you an idea of the structure of this data set, is I'm going to graph this categorical variable called latitude zone, and just to show you how many samples we have in each group. So it's some number very close to 400 samples from each group. These 3 groups are high latitude groups toward the poles, middle latitude groups, and then low latitude groups, which are toward the equator. And again, about 400 samples from each of these. I could look at these same data as a frequency bar plot and just see, so close to equal sampling from each region here. If I go back to the dot and line based graphs, and instead of looking at this categorical latitude zone, I'm going to look at this average temperature anomaly split by these latitude zones. We can see something important about the data right away in looking at this. And if I'm going to add descriptive stats on here for a second. And right now you're looking at box plots beside the data that are showing the median and the interquartile, and the whiskers are showing the full range of the data. So, right away you can see that the data has a much higher range in high latitude, and you didn't need the box plot to see that, but it just illustrates it. But I also highly recommend showing students dot plots for numeric data, because you'll see if I hide those and we just look at box plots, we get the same story. And if you're familiar with looking at these kinds of plots, you kind of know what that represents. But I think that students might not have the best idea of what the raw data looks like that is underlying that until they look at those points where they can see each measurement spread out like that. This gives them a much richer picture of what's going on. We could also look at, like, say, a mean and standard deviation of what we're looking at now, and to kind of quantify that. And you can see that the standard deviation in the high latitude group is much larger, and I've got it up on the table on the right. We can see in the high latitude groups, the standard deviation is like 1.38, and in the low latitude groups, it's 0.513. So it's quantitatively much smaller. But the interesting thing with this is, to ask students, well, okay, well, what does this mean in terms of real life? And to do that, they'll have to maybe read about that variable of average temperature anomaly and saying this is how far from the average over, I think it was a 50-year period in the middle of the data set, of how far above or below average each of those temperatures are. So positive numbers are much warmer than average days, and negative temperatures are much colder than average days. And I actually can't remember if this data is each data point is a month, or if it's actually is it a year, a month, or a day? Blake, I'll have you look at that while I'm going into this. But it's showing you for whatever the time period is that's been recorded, are these temperatures far above average or far below average? And what we see is you just get massive temperature swings as you get toward the poles, the high latitude zones, and the temperature becomes much more stable as you get toward the equator. So that's kind of the key observation of this figure. The next big question in this data set is what's happening over time. And so to do that, I'm going to add this variable of year, and you can see I clicked show, and it's queued up on my control panel, but it's gray because it's not showing right now. And I'm going to click it to be my new X variable, and we can look at the trend over time. And we can look at these temperature anomalies, these days that are greater or less than temperature wise than the prediction for that day. And if we add a regression line, we can see this overall trend toward a warming climate in the data. I think particularly sort of something that might be just a bit alarming is the way that you almost have, you have this linear fit, but you almost get like this sharp drop in the tail at the bottom end of it as we go back toward 1850 or 1850. And we see this like sharp kind of upswing and peaks that have happened, in recent times. Like I'm hovering on this 2020 data point, which is way up here, or this, I think this one's 2021, which is also, the two highest data points in the data set are 2020 and 2021, and we don't have 2022 data in here. But just like we did in the last data set, we might choose to add this third variable of latitude zone on top of here. And when I add that, we've got these three, contrasting colors with high latitude, middle latitude, low latitude. And if we check this box over here to the right to group by that variable, group by the Z variable, we can get separate regression line for each of those. And you can see that the line of best fit for the high latitude is much steeper than the line of best fit for the middle and the low latitudes, the orange and the green. There's also been some choices that we've made that we've baked into this data set in terms of the art of graphing to make this a little bit more visible. Within Data Classroom, like our default size for points, I think is somewhere like, I think it's close to like 13 point or something. And if we turn these points up and make them bigger, you can see how it can be tough to discern the individual points. I think these points that are this big visualize really well with small student collected data sets. But a lot of times when you've got, a pretty big cloud of data like we do in this one, when you shrink them down to a smaller size, it makes everything just a bit more visible in the data set like we did here. So that's something we've done with this graphing to make that more visible. you could make them very, very small and then, see them just kind of as a field. But I think somewhere in between, maybe about like this, looks good to see the trends there. Okay. One thing too, I didn't even talk about, one thing that this data set can be used to illustrate a topic in earth science or environmental science called the ice albedo effect, which could be the sort of the causative explanation of this trend that we're seeing in the data. We can clearly see that it looks like the high latitude zones are where the ice caps are have greater temperature fluctuations and are trending toward this higher temperature faster than the other zones on the planet. And this is exactly the kind of data we would expect to see based on the hypothesis of this feedback loop with the ice albedo effect, is that as the ice caps melt, more area of snow cover melts as well, less solar radiation is reflected away from the planet and back into space. And so it accelerates the warming. The low latitudes and the middle latitudes never had any, or haven't had any snow cover in this time period in the data set. So they're not experiencing that. They're just sort of warming as the Earth warms, but the high latitude zones may be warming faster as less solar radiation is reflected off of snow and ice. And these data are certainly consistent with and evidence for that hypothesis as well.
To chime in from the peanut section, just wanted to confirm that the average temperature anomaly, there are a couple different ways to measure that, but the way used in this study was where you take a measure on a given day, and then you compare that to the monthly average over that 30-year period. So they're randomly sampling on different days at a given weather station, and then compare that to a monthly average.
Yeah.
I just want to add, Aaron, one of the fun things with this one too is you really have to focus on students qualifying which graph they use to answer different questions. So it's just funny how if you use the visual where you have the x on the x-axis, the different latitudes instead of time, right? The means are all relatively similar. I think if you run an ANOVA on this, you get a result that is not statistically significant, which if taken strictly at the literal value would suggest that there wasn't really a difference between the average temperature anomaly across these three latitudes. But very clearly, like looking at the data, there's more to a story. There's more of a story there. And that's you can prove that by using a graph-driven test, looking at the linear regression.
Yeah, and right, and again, and this is one where like you could run ANOVA. I don't think you need to. I think the visuals are pretty powerful, where you can see that when you look at overall, those means are just not very different from one another. And the statistician in me also feels like I need to point out that this would violate one of your ANOVA assumptions of equal variance across the groups you're comparing. But again, that's also one point I try not to get too hung up on those kinds of assumptions, especially when you're in exploratory mode with the data set, because it in that case, even though it violates those assumptions, you more or less get the answer that supports what the reality of what you see here is, that we don't see a big difference in the means between these groups. Yeah. Okay, well, with that, let's head back to that, and we'll frame our third and final data set of our evening here. And this final data set is, I think this is a cool one to study in combination with one, or have students work on in combination with one of those bigger long-term data sets, because this is a very short-term data set on a much smaller scale. But instead of pulling data from the environment and sort of observing data and using that to draw conclusions, this is a targeted experiment related to climate change, where students are manipulating some variables intentionally to kind of predict what effects climate change might have. And so to give some context here, this was conducted at Michigan State, and one of the co-authors of this study is a dear friend of Data Classroom, Liz Schulteis, who works out of the Kellogg Biological Station at Michigan State University. She's also one of the co-founders of Data Nuggets, and we've had her on the program a time or two as a guest speaker. And what Liz and her co-authors did in this is they planted a plant called Dame's rocket in a field. Dame's rocket is a relative of mustard plant. And they randomly assigned it to these two different treatments. And one of those treatments was just ambient temperature. So they planted it out in an experimental field and it experienced ambient temperature. The other one, they elevated the temperature, and they elevated it just a couple of degrees to fit with predictions of climate change at one period of time. I can't quite remember if they went, and again, this could be another detail to track down. Blake, I'm losing my memory here. But I can't remember if they went to the amount of climate change. I think it was roughly what's predicted for about 100 years in the future, and to see what effect it would have on flowering time in the Dame's rocket. This is a good data set to talk about selecting the appropriate graph for your research question, because there's quite a few questions you can ask in this. There's maybe two that are kind of key research questions that you could look at. It's also a great one to use graphing as a gateway to statistics, because the graphs will lead to very different statistical tests. And it's also a way that I think you can use this graph to explore experimental design, and you can illustrate a couple of things about the experimental design. And when I jump into the data set, that's what I'm going to do first, and look at how you can see some of the signatures from the experimental design in some of the graphs. Then these aren't going to be graphs that answer the key questions, but they kind of answer the question of what the scientists themselves did. And thank you, Blake. You want to give us that answer? Thanks for answering that question.
Yeah, just confirm they were using the projected increase in temperature in Michigan by the end of the century.
Okay, so not 100 years in the future, but by the end of the century. And this data set is called Springing Forward, and it is a digital data nugget. I want to take a second to talk about what the digital data nuggets are, because I know we had at least one question from a real person out in the wild today about where can I find the data sets from the digital data nuggets. I just want to say that first off, these digital data nuggets are adaptations of the pencil and paper data nuggets, which exist on the datanuggets.org website. Though those are great activities. They're strictly paper and pencil, no technology required, and those exist as their own entity. The digital data nuggets are adaptations on Data Classroom that we've done in collaboration with Data Nuggets, and the assignments for the digital data nuggets. So what I'm pulling up now, these are adapted slightly so that you carry out the entire activity within the digital environment of Data Classroom. So they're not fully identical to the pencil and paper activity, but they're very, very similar, and they're certainly exploring the same core data set. Very often, the Data Nuggets data sets were simplified to make them easy enough for students to plot by hand. And those data sets, when they're in Data Classroom, very often it's like the full data set that the scientists used, because with the power of a computer, students are able to handle more data. So I'm gonna jump over to the graph view. I've queued a bunch of these variables up on the control panel, and I'm going to do some of these exploratory things to kind of look at experimental design. And so the first thing I'm going to do is look at treatment. And so if I add treatment on the Y on this circle and dot and line based graphs, I can see that I had 36 samples in the normal treatment, and then 34 in the heated. And by normal, this just means the ambient temperature in Michigan. I could also look at these data as a frequency bar chart. I could also look at these data as a pie chart. It doesn't really matter, which way you're looking at them. But this is nice to ask, basic questions about the experiment. How many plants in each group did they test? We could also look at this variable of ring, and what this ring is. When you read the assignment description, they place these artificial heating rings out in the field, and they had, you can see they had 8 rings, and they had roughly 9 or 8 observations per each ring. And what these rings are is they're just heating elements that were these big round rings, and they would just place them out in the field. In the control treatment, or the one we're calling normal temperature, they were not turned on. And in the treatment that we were calling the heated, they were turned on to warm the temperature roughly 3 degrees. And if we look at this, I like this graph of ring by treatment, but I'm actually going to pop over and look at it in this format, where you can see, or even might even do, I like maybe this one, plant by treatment, plant by treatment, and you can see how many plants they had in each of these. And so you can see they have, 4 plants in each of these per ring and plant number. So these help you kind of see the structure of the data set, and how these data are set up. But I'm gonna go back and look at one of the central questions, and this is, I'm putting date of first flower on Y, and I'm putting treatment on X, and you get some pretty strong results here, where we're looking at the heated treatment, and you can see the day of first flowering. They started flowering almost right away, ranging from day 1 up to day 11. So these were, these were flowering really quickly. In the control treatment, or the normal treatment, they ranged, the date of first flowering range from 12 to day 19. And when you get a result like this, where you have completely non-overlapping data between the groups, you don't really need statistics to tell you that, yeah, something different is going on. We could apply descriptive statistics like a median or a mean, and we can see the mean for the heated group is about day 5, and the mean for the control group is about day 16. We could also run the t-test, and this graph-driven hypothesis test here will explain that, given these assumptions, with this variable on X that has 2 values, and this variable on Y that's numeric, and before we give the output, it will give you this sort of textbook like pop-up to explain why we're doing a t-test and how does it work. And then it'll give us our result, and as expected, we have a very, very small p-value, less than 0.01, which is as low as our display goes here. And it means extremely strong confidence that the groups are different based on these data. There are some other questions we might ask, and we might ask the question of, okay, so we know that plants are going to flower earlier if the climate warms 3 degrees, or at least we have strong experimental evidence indicating that. But what our plants, are they actually going to survive that 3 degree temperature increase? What do we know about survival? And if we look at this variable of treatment against this variable that's called alive ? And we look at that, and we look at this categorical bubble, we can see the breakdown. We have the control groups on the left, and we have the heated groups on the right. And then we have the plants that lived, the bottom, the yes, and we have the plants that did not live, the no's, on the top. And you see 3 times as many plants that died in the heated group. I think if we switch over to the graph made with rectangles, we look at this, and even I like to do this. I go in the appearance menu, and I'll stack these and I'll stack them as a proportion. So now the y-axis has become percent. And I can see that, you know, the heated group, 26.5% of the plants died, and the control group only 8.33% of the plants died. And if I run statistics on this, we get a, you know, we do not get a recommendation for a t-test anymore because it just flat out won't work with that kind of data. But if we look at the chi-square test of independence to see if the outcome of alive or dead is dependent on the treatment, you know, we see that in fact that we get a p-value of 0.04, meaning strong confidence there is a relationship. You'll also see we get this little warning from Data Classroom letting us know that, you know, we have a really small sample size here. And as a general rule, you want most of your combinations to be represented at least 5 times in the data set to feel good about, you know, your conclusions you're drawing. And in this case, you know, if I unstack this and I go change it after a proportion, you can see that we only had 3 non-survivors in the control treatment. And so, you know, it maybe calls that statistical result into question. I'll tell you, as a scientist, I would have no qualms whatsoever about, you know, reporting that chi-square in a paper on this. This looks like a pretty clear result to me. But that's the kind of thing that, you know, we've built into the software to help students who are not experts to maybe take a second look at something. And it, you know, depending on where your students are at, it could be a jumping off point for you know, more sophisticated discussion of the statistics. So I see we are running short on time. So I guess I'll just ask if we have any questions before we wrap up for the night. And I'll say we will be sending out the recording to this to anyone who registered for it. So you can look out for that in your inbox within the next week or so. We'll get that out to you. As always, thanks for coming to talk data with us. We really appreciate you giving up an hour of your day to sit with us and look at some data. If you have any questions about working with data, feel free to reach out to us, and maybe I'll put up that contact information here that we have on our last slide. So if you need to reach us, I'm Aaron at dataclassroom.com, and Blake is Blake at dataclassroom.com.
We had one quick question. I assume it was about that springing forward data set. Kristen's asked, did the heating affect both the soil and the air temperature?
It's a good question. It affected the air temperature because that was part of their treatment. Is they set the heating elements so that it would raise the air temperature within the ring that the plants were planted. It would raise it 3 degrees. So it most definitely affected the air temperature. I don't know if Liz and company had any data on the soil temperature. Something tells me they probably did. We don't have it in this data set that's here. But I would imagine they recorded that, and I imagine it was, you know, buffered as soil would do with temperatures, that it wasn't, you know, it wasn't a full 3 degrees warmed, but I would not be shocked if it was warmer than outside of the rings or in the controls. Okay. With that, Blake, I will sign off and say good night.
Sounds good. Take care, everybody.